We have these meetings in person on the UC Davis campus. Unfortunately, because of the current situation, we've decided to transition things remotely, but that gives us an awesome opportunity to reach out to more people. And before I get into any content about about like what this sort of meeting is about, I wanted to sort of take the opportunity to introduce the organization. So we are Quantum Computing at Davis. Samarth, if you want to go ahead and introduce yourself.
Hi, everybody. My name is Samarth Sandeep. I'm the president of the Quantum Computing Club. I started the club with some of my friends at UC Davis 2 years ago after going to the Rigetti Hackathon. And I'm really excited to see all of you and to hopefully get all of you into quantum computing stuff. So I do research in quantum biology. So I do research particularly in how we can use quantum computers to better model biological systems. And particularly a lot of my research has been recently around how we can model the coronavirus spike in a better way using quantum computers, and then how we can use that model for better energetics modeling of potential drug candidates. So if you're interested in quantum biology stuff or anything similar to that, please feel free to send me a message or ask in the chat.
Miranda, you want to go ahead and introduce yourself as well?
Yes, I'm Miranda. I was the VP, joined with Samarth 2 years ago. I am currently in an experimental lab, although it's now theoretical, with a professor here on campus in studying quantum color centers. So if you're interested in quantum nanophotonics, I'm your person.
Torin, you want to take the helm here?
Yeah, so I'm Torin. I'm a workshop director here too, and I'm part of Samarth's research team at quantum biology. Good background also in software engineering. So you see if you're interested about where those two intersect, kind of talk to me if you want to learn more.
Tina, I think if you can hear me, you can feel free to introduce yourself as well.
I'm just the director of propaganda, and I'm just here to get the word out.
All right. Well, that's Tina for you. And I guess I should introduce myself as well. My name is John. I'm also a workshop director here. I'm not doing as much sort of phenomenal work, but my main role is to develop a lot of the educational material that you will be seeing throughout the quarter, throughout subsequent weeks, to help you sort of understand quantum computing better, some of its applications, algorithms, et cetera, et cetera. So if you're interested in that kind of stuff, please feel free to stick around and check out some of the materials that we have. All right, so we have a couple of objectives as an organization. So our primary objective is we want to foster knowledge of quantum computing. So what is it? How can we use it? And how can you sort of further explore this field? So we don't just want to just give you the tools and say, okay, this is the limit of what quantum computing has to offer. It's an ever-growing field, and we want people to be able to figure out what they're interested in and how to apply that technology. But more importantly, I always talk about this idea of having a kind of quantum intuition. And it's this idea where you can translate a classical problem into a quantum one. So we have to understand that quantum computers operate in a very fundamentally different way from traditional computers. And the ability to translate certain problems that may be difficult or even considered impossible for classical computers onto quantum computers is a very incredibly powerful skill set to have. So that's one of our objectives as an organization. And you should understand the properties of quantum computing that make it so useful, and what model of computation works best for your problem. As you'll see, quantum computing is really this umbrella term for a lot of other technologies which exploit quantum mechanics, but do so in some very different ways. And I'll try and we'll make sure to touch up on that near the end of this meeting. So, and if you have any questions, feel free to put it in the chat, and I will address it. I have the chat window up to my right here. So if anything comes up, I will do my best to see it. All right, so here are the objectives for today. So I just wanted to give sort of a quick primer on some quantum mechanics, some properties of quantum computing and their current applications that really fascinate people, and quantum computing hardware, which I think will be very invaluable for people sort of moving forward into this field. So quantum mechanics has a particularly interesting origin. And I put this quote up here. It's one of my favorites. There is nothing new to be discovered in physics now. All that remains is more and more precise measurement. This is wrongly attributed to Lord Kelvin around the end of the 18th century. This actually comes from, I think it's one of the lab directors from the University of Chicago in the early 20th century. That's the true origin of it. But nonetheless, we were sort of reaching a point more in the late 18th. Excuse me, that should be late 19th, not late 18th. But around that time, physics was sort of reaching, or classical physics was reaching this kind of sort of plateauing point. Like, okay, we've sort of figured everything out. Everything sort of falls into place, and it's going great. Unfortunately, we had a number of experiments that really that really proved that classical physics was missing a bunch of key components. And so I highlight these here, the ultraviolet catastrophe, the photoelectric effect, and the Davison-Germer experiment. And I'll go into a little more detail about what that is, I think in the next slide or the slide after next. But basically, we started encountering these scenarios where classical physics started to completely fall apart. And our best explanations of these phenomena using classical physics didn't work. They simply produced completely nonsensical results. So something was up, and we had to sort of get to the bottom of it and figure out what it is. So that sort of gives birth to this idea of quantum mechanics, this entire new field of physics, which sort of shook the foundation back then. So the first property that I want to look at is superposition. Superposition is this idea that so physically, if I have like a quarter or something, I can only assume one of two. If I lay the quarter on the table, it can only assume one of two states. So it's either going to be a 0 or it's going to be a 1. There's no sort of in between. It's like our computers when we store binary values. It's either going to be a 0 or a 1. There is no other in between. And so this back in the early 19th century, or late 19th century, we had the Thomas Young sort of double slit experiment, where you have used light, and light produces a diffraction pattern between these two slits. Unfortunately, I don't have the whiteboard in front of me, but I could illustrate this much better. So back then, people thought, okay, so light can either be behave like a wave or a particle. But Davison-Germer, they're two scientists from Bell Laboratories back in the early 1930s. They figured out, wait, if I shoot electrons, which we believe to be these discrete particles, they also have the same behavior. So they figured out that it's not either, but it's both. So light can both be a wave and a particle. It's this superposition which collapses once you make some observation, you interfere with that quantum system. All right, so that brings us to the second property, entanglement. Einstein himself famously said, when he first saw like this idea of entanglement, he called it spooky action at a distance. And he was not particularly happy with the idea of quantum mechanics to begin with. But unfortunately, just because he's unhappy doesn't mean that we can completely omit the existence of quantum mechanics. So we call this spooky action at a distance. And basically, it's this idea that I can create I can create two particles or even a group of particles. And through this group, I can split them. So if I have like 50 particles that are entangled, and there's a way of doing this, there's a methodology for it. And you sort of split them through space. So I put one half of those particles on one edge of the galaxy, and another half of the particles in some other remote corner of the galaxy. And I perform some measurement. I interfere with the system. There's an instantaneous sort of interference on the other side. So that's this idea of entanglement. If you know this satellite here, the reason I put this picture here is this is a very interesting and absolutely amazing experiment going on. I think it's being hosted between China, one of the cities in China, and Vienna, and it's using sort of this optical entanglement. It's called QES. I think it's quantum experiments, quantum experimental satellite system. That might be the name for it. QUESS, and it's amazing. Just they're pushing the limits of really how far you can sort of split this quantum system and still observe entanglement. So that's if you want to look into that, I highly encourage it. And then we get to the no cloning theorem. Now, this isn't exactly a pure quantum property so much as a consequence of those two other properties, so superposition and entanglement. The no cloning theorem isn't really as cool, and in a lot of explanations they will intentionally omit this. But the reason I want to bring it up is this will be your sort of introduction to some of the barriers of quantum computing. So this is a difficulty that has to be overcome through just a lot of ingenious work. And the no cloning theorem basically states that we can't copy an unknown quantum state onto another quantum state. So why this has such a big implication, and why I even bring it up in the first place, is, if we look at classical computing, if I want to make a copy of data and I need to copy this data for, say error correction, or I just want to sort of shuffle a copy around, well, that's very trivial to do with a classical computer. I just take this one wire and there we go. I have two wires. It's a trivial example, but in quantum mechanics and in quantum computing, we cannot do this. This is a forbidden operation. So as a result, we have to exploit things like entanglement to sort of try and imitate some kind of result that we would get through this splitting. And this is a quantum circuit. If you don't know what that is, don't sweat it. We do have future workshops that will go into considerable more detail about it. But the idea is no cloning theorem is something you have to be aware of as you develop, say certain quantum algorithms or use a quantum computer. It is something that is particularly tricky to work around, but it does not make quantum computation impossible. It's merely it merely requires you to think in a different way. All right. So if you want knowledge of more fundamentals, we do have an organizational GitHub. It's called Quantum Computing at Davis. You can go ahead and check out this link here, or go to the link yourself. And there is a set of workshops that I've built from the prior quarter for people who want a sort of stronger understanding of how the math plays into these fundamentals and how the math is supposed to be beneficial for quantum computing. And it's very introductory stuff. It doesn't touch on algorithms, but for those that are just beginning, or for those that really want to get your hands dirty, I do strongly encourage you check this out. So with sort of these properties out of the way, and once again, I'm always open to questions. So here's what we hope that quantum computers can do. I've mentioned all these really odd and sort of mysterious quantum mechanical properties, and we have, we want to use those properties to perform useful computation. So we use quantum mechanics to perform stuff we want computers to do. And there are different approaches to do this. I'll make sure to touch up on this as we sort of near the end of our little meeting here. But we want to see one of the following. These are pretty much the two fundamental things that we really want quantum computing to show. We either want to make something that is impossible possible, or we want to make the very slow very fast. Now, for those that are, much more mathematically rigorous and more experienced in this field, you are probably experiencing some discomfort at how greatly I've oversimplified things. But this is essentially what all the terminology out there really wants to see. So when I mean we make the impossible possible, there are some algorithms or some problems that we consider just infeasible on classical computers. By classical computers, I mean the laptop that I'm sort of hosting this meeting on, the phone in your pocket, things that still use silicon-based logic, ones and zeros, so on and so forth. So quantum computers may be able to make this sort of impossible calculation possible. And then we also want to see this very slow become very fast. So one example of that is if we try and simulate certain molecules or certain chemical systems, there is a exponential growth and difficulty when we try and do that. But quantum computers sort of have this very desirable sort of linear growth property. So, and I'll get into a little more detail over that. But basically, we really want to see these two properties. And if you're using a quantum computer, you really want to exploit these quantum mechanical properties to obtain this desired speed up. So that's a huge thing that we really want to see. So here are some sort of key applications that are happening right now. Like, these are not theorized; these are being heavily researched right now and are already showing a great deal of fruition. So molecular simulations. So this goes back to what I said about the very slow being very fast. In traditional computing, if we try and do molecular simulations, every time I add another atom, the resource consumption, or the rate of resource consumption growth, is exponential. So it's like, 2 to the n or something to the power of n. Whereas, quantum computers have this really nice property where the resource growth rate is linear. So if I add another atom to a certain simulation, it doesn't really use as much resources, which is very nice. This isn't perfect right now. It's still being actively researched, but we can. One of the reasons for that exponential growth is because we are trying to model, superposition and entanglement, which you do see in molecular systems using classical computers, and that's not really a very efficient way of doing things. Whereas quantum computers are sort of home territory. We can cleverly exploit superposition and entanglement to sort of speed up these simulations to make them more efficient and sort of reflect reality a lot more accurately. If you really want to know the origin about that, I strongly encourage you to check out some of Richard Feynman's original lectures. He came up with this idea like, if you have a quantum computer, we can simulate quantum systems. That was sort of one of his sayings. And I say that verbatim. Machine learning is sort of a very hot topic right now for quantum computing. The reason being is a lot of the algorithms can exploit, once again, superposition and entanglement. Finance, that's not exactly my forte, but I know JP Morgan and a couple of the larger financial institutions will use it for modeling or trying to make sort of predictive models about future market behavior. This is on the table right now. It's not a paper floating around. This is something that there's an actual coalition going around for it. And cryptography is probably the field that quantum computing is most well known for, or most renowned for, because the moment you mention quantum computing, I guarantee you there's got to be some person who will say, oh yeah, Shor's algorithm. And you're right, Shor's algorithm provides a incredibly fast way of doing large integer factorization. And this idea that factorization is very difficult is key to literally a great deal of the encryption systems today. Especially what we use on the internet. And, there are always these sort of scare articles or spook articles that come out saying like, oh my goodness, quantum computing is going to be the end. But as you'll see very on, like our concern is warranted, but it doesn't have to be that high. And another thing is key distribution. So quantum computing has sort of kicked off its own entire field of cryptography. In fact, there's a lot of talk now about what we call post-quantum cryptography, PQC. And it's getting a lot of traction because a lot of the traditional tools to develop new encryption systems literally fall apart. Like once you put a quantum computer to attack it, it's almost trivial for a quantum computer to try and break these things. So as a result, post-quantum cryptography focuses on ways that a quantum computer, it's difficult for a quantum computer to attack these systems. So that's where we get things like quantum key distribution to securely distribute encryption keys, and that's part of the KESS experiment with the satellite and sort of photon entanglement. But I digress. So the cryptography is definitely a field that has seen immense growth due to the existence of quantum computing. Okay, so here's where we get sort of to quantum computing hardware. And I understand this might be a little advanced for sort of an introductory talk, but it's just think of it as a primer. Like as we sort of go on forward, we will have the chance to explore these different models. And I just wanted to sort of put this in your ear, put it in the back of your head. It's food for thought. It's definitely food for thought. The problem with saying like, oh, this, X is a quantum computer or Y is a quantum computer is that we're still stuck in this sort of classical way of thinking. So when I say like X is a computer or Y is a computer, our brains immediately think, oh, it's like a silicon-based computer. It uses ones and zeros. It performs arithmetic, multiply, add, sort of bit shifts. That'll definitely be something to sort of be careful of, because when we call something a quantum computer, the restraints are a lot looser. We're basically just talking about a system. We want to distinguish between these different approaches to quantum computation. So basically any computer that uses entanglement, that shows superposition, that shows that shows quantum properties, we call a quantum computer. But even within that realm, there are different approaches. And the way I think of this is, like normal computers, we have the x86 architecture. So that's like for desktop computers, but your phone uses like ARM or some variant. So that's another way. And, it's just a way of a mental model for you. So I will tell you that one thing that all quantum computers have, that every quantum computer must have, are qubits. And qubits are the fundamental unit of quantum computation. It's very similar to how classical computers, we have bits, right? 8 bits make a byte, and you have 2 to the something. Good. Off the top of my head, megabytes and gigabytes. Whereas, for qubits, we just have, for quantum computers, we have qubits. And I put anything in bold here. So anything that exhibits quantum properties. So it doesn't just have to be atoms. So like in the very early days of quantum computing, we did exploit trapped ions. You make like this sort of, you can use this electromagnetic field, this specially oscillating electromagnetic field, to manipulate an ion that is literally trapped in a very small area of space. But over time, a large variety of methods for creating qubits have come up. One of them is the superconducting Josephson junction, and that itself has several variants depending on the circuit geometry. And this Josephson junction it does not require an ion to be trapped. It's a lot easier to fabricate because a lot of our traditional methods for doing silicon fabrication for computer chips can be repurposed to perform the sort of Josephson junction production. And light is also something that's very, very interesting. It's still being developed, not as sort of mature as I would say as the Josephson junction, because it itself has some rather special limitations. But light is very advantageous for a number of reasons, and you will see that in the next slide. Now, how these qubits are used can vary significantly, and the variation in the usage of these qubits is part of the reason why there are different models of computation. So the gate model is probably one that, for those who have used quantum computers before, are very familiar with. The gate model is, let's see if I go back a little. Okay, yeah, this is the gate model. So each manipulation on a qubit is represented as what we call a gate. And the great majority of existing quantum algorithms can be implemented in this gate model. It's sort of like the equivalent of logic gates in our classical computers. But there are 2 other models here, and these are not as complete. So I always make the distinction here that the gate model is what we could consider like a universal model, or near universal, whereas these models still use qubits, and these qubits still satisfy quantum mechanical properties, but they do it in a radically different fashion. So Gaussian boson sampling, this also uses light. Light is a kind of boson. It's just a class of particles. And the Gaussian boson sampling, it's a little tricky for me to explain here, but it exploits a particular statistical distribution problem that it can do much faster. And the idea behind these non-gate models is that if I have a problem that I can map to what they solve very quickly, then I can experience some kind of speed up. So Gaussian boson sampling is one of them. And adiabatic quantum computation, that's a bit of a mouthful, otherwise known as quantum annealing, is something that D-Wave offers. And this uses the Josephson junction model. So, it's a superconducting chunk of silicon, essentially. But it does not use gates. It uses this idea that if you initialize a certain quantum state in some kind of energy Hamiltonian, and you sort of change that energy landscape, the Hamiltonian, slowly, hence the word adiabatically, you will stay in an ideal minima. So if you change your problem into some kind of minima, then you can use like a D-Wave computer. And the reason why I know a little bit more about that field is because a great majority of my experimentation has been on this platform. And there are some, all these, platforms, why do we even bother with all these different platforms is because there are some problems that we need to tackle. So one of them is incredibly sensitive to environmental disturbances. So what do I mean by this? If we go back to this Josephson junction, it's a superconducting piece of metal, superconducting piece of silicon, to be exact. And the problem with having anything that's superconducting and having anything that's sensitive to EM radiation is if you don't have a very tightly controlled environment, stray radiation or thermal fluctuations will cause you to get false or erroneous results. So that's something that has to be controlled very tightly. Now that's the reason why there are proponents who support sort of photon-based quantum computation, and photons are not as sensitive to EM, electromagnetic interference or temperature differences. Remember, it's just a finely controlled beam of light, essentially. But even that has its own problems, and this is another one. Error rate and timing sensitivity is also something that Josephson junctions suffer from. Basically, because you're in that superconducting environment, very cold and whatnot, the amount of time that you have for a computation is limited. And what do I mean by like limited amount of time? Is the longer you're doing something with that junction, the higher the chance some error is going to get into your computation. So if you look at a lot of research papers, they always stress like, oh, it only took me like a fraction of a microsecond to do this manipulation. And that's good. The shorter the time, the better. But platforms like that use light, like Gaussian boson sampling, or those that use ion trapping, have very long lifespans. So this isn't really a problem for those platforms. But the trade-off is that they're not very scalable. So the problem, like ion trapping, historically has a very long history. But as I mentioned, it's this it's this electromagnetic field that has to trap a literal ion in some special state, and that is the growth rate of hardware required for a problem. Like if I add another qubit and then another qubit and I keep adding qubits, is exponential. It starts to become very disadvantageous to keep expanding this. So ion trapping is not, for scalability, it's sort of frowned upon, but for long-lived qubits, so for performing calculations that require a very long period of time, they are incredibly advantageous. So that's why we want them. So those are, these are just some of the problems. And these problems kind of highlight where we are today in terms of quantum computing, which is what we call this sort of NISQ era, or noisy intermediate scale quantum computing. So I'm going to sort of jump over to this slide real quick. This was produced by Rigetti, and this is a very nice sort of visual depiction of what's going on. So our computer, we're starting to reach this NISQ area. This is where we are today. And the idea behind NISQ is this the last, okay, yeah. So we are in this sort of in-between period. So in the early days, maybe in like the 90s and early 2000s, we had computers that were maybe like 3 or 4 qubits, and we could use a traditional computer to simulate those qubits to make sure that our results were correct. And this wasn't too hard to do. Your computer, your phone can handle a handful of qubits. It can classically simulate those qubits. That isn't a problem at all. But once we get to this sort of, we start branching out from that, right? We want more powerful computers. We find ways to make the hardware more scalable, like Josephson junctions. And we're starting to reach this kind of tricky little position here where we're not at the point where the computers are totally fault tolerant. And what does fault tolerant mean? Well, it just means that if I have an algorithm or if I have some quantum program, I don't want any errors introduced into the program, or the errors are at such a low level or a low number that they are very easy to fix. And we are not at that point yet. We are not at like 100% fault tolerance, but we're already branching out from these normal, from just having like 5 or 6 qubits that we can still simulate. So once we hit this barrier, it's I think roughly around 50 qubits. Or approximately 50 qubits, it starts to become impossible to classically simulate. Even with our best supercomputers, this starts to become just a very incredibly difficult thing to simulate. So that's this NISQ era that we're in right now. So basically here we are. So this is the physical error rate. So our errors are usually above here, and then the number of physical qubits. So, as I've been saying before, we have already exceeded, 5 to 10 qubits. That's sort of, trivial. Like our computers, our normal computers can simulate the same behavior, which is desirable, because if we're developing algorithms, we need some kind of safe base references and if we're doing our computations correctly. So that's one of the main things that we want here. And we're still in this NISQ era, so we're starting to approach 100 qubits and 100 plus. That's very feasible, but there's still noisy qubits. And once we start hitting that 50 to 100 area, we can't classically simulate that stuff anymore. Like even our best, the top supercomputer. So even like the one that China has, Tianhe like 2, cannot do that anymore. And we're sort of reaching this territory where we need to make sure that the algorithms work the way they need to, but it's tricky to find a safe base reference. So NISQ has really prompted development in what I would call quantum error correction. Quantum error correction it's sort of a field where we're concerned about, because of the restriction of the no cloning theorem, we need to find a whole new set of algorithms to correct and to make sure that the integrity of the data we're processing isn't compromised by, thermal fluctuations or by some hiccup inside the actual Josephson junctions and what platform you have. So we're going to stay in this NISQ area for quite a while. Now, this slide is from Rigetti, mind you. So Rigetti is tooting their horn, saying that within 5 years, we can hit this sort of fault-tolerant sweet spot. This is this is what we really want to see in quantum computing, where our physical error rate really starts to decline to these sort of really low levels, and we can focus more on using this large number of qubits at our disposal. So this is we're in very exciting times right now. So we still have noisy computations and we still have a limited number of qubits, but it will only be a matter of time before we start hitting this fault-tolerant quantum computing, in which case we're starting to see much more ruggedized and more capable quantum computers. All right, so that's what I have in store for you guys today. I think this was like just nice primer material, I'd say, for maybe some of the stuff we'll go over in the future. I'm going to sort of keep the meeting open. The meeting only ends at 6 sharp. So if you have any questions or maybe any corrections that you wanted to make to the stuff I presented, feel free to raise your hand, unmute yourself, and talk freely. I guess I'll let Amir go ahead with his question.
Yeah, it's great that you left it on this slide, because this is the slide I was wanting to ask about. I mean, obviously there's an implied comment in this, but I'll go ahead and ask it as a question. So yeah, with this slide, I know it's, I think you mentioned, courtesy of Rigetti. Obviously, they have an interest in having near-term quantum computers work. But the part about within 5 years, I'm curious your own personal take on that. And in a realm where, if you follow on Twitter, there's quite a lot of commotion about any kind of predictions like that. Maybe you're aware of the Twitter account QBD. Yeah, I'm just curious if you could speak to that a bit.
Yeah, sure. So I'll give a very brief disclaimer. My social media usage is incredibly limited. Usually, like when school kicks in, I always try and make it a habit to try and reduce the amount of time that I spend just sort of scrolling through. But I do understand, as you mentioned, there are always these market predictions about where quantum computing will be, and any breakthroughs always spur a lot of activity. So personally, this within 5 years. So this is something that I believe this is Rigetti's number in terms of what they think they can achieve, and then, it may or may not be possible. With quantum computing, I've always been very hesitant to sort of fully invest myself in one sort of belief or another. So I don't really have too much to speak on that platform. So I'm not familiar with that Twitter account that you did mention, but it's like Google came out with that announcement where they finally have some proof of this elusive quantum speedup. So that, it's or quantum supremacy, which as far as I've heard, the creators of that term kind of regret the using the term supremacy, because it's people conflate it with the wrong thing that they were going for. But the moment that news hit, people sort of see there's more and more of viability, and then it's almost a war on two fronts. I mean, there's hardware, we're trying to get better and better hardware, and there's software. Like even today, we're trying to figure out like, oh, what is this? This is kind of cool. What's the maximal application that we can get out of it? So 5 years, to me seems a little too optimistic. It might be a little too optimistic, but this again. Then again, there's always there's so much development. It's very hard to make any solid predictions about what's going to happen. I just saw a news article, I think it was on Wired, where some company's trying to shoot for 1 million qubits. So that brings them all the way here. But I don't know,
Yeah,
in terms of
quantum.
yeah, PsiQuantum. Okay, Samarth is very
With
familiar with that.
the M12 funding, yeah.
Yeah, so I'm like, my brain is blown here, and I'm looking at like I don't know what they're going to do with this physical error rate, because we're still floating at this 10 to the negative 2 something errors. So but to recap, to answer your question, I'm not too, I have no predictions whatsoever. I always just remain as open-minded as possible, and I just see where it goes.
Yeah, you did preface that this is Righetti's slide, and believe me, I also am very much wanting this to be the future that occurs. I think I've been tempering it a bit more, just because I'm the more of the like QC person, or quantum computing cheerleader at my company, and I'm just careful to like set expectations correctly for what we might see in the future, because after kind of going out to social and seeing how some of these articles are landing on people in the field, it sobered me up to adjust my own language personally about what we're going to be able to do with quantum computing in the near term, and it's certainly awesome, all the efforts that are being tried, but I just I guess I'll say I'm optimistically skeptic. Or skeptically optimistic. That's probably better.
No, that's definitely a very healthy attitude to have. I mean, it's there's definitely a lot of interesting development going on. It's sort of this sort of trickle down where we see a lot of the work that was originally reserved for research and theory make its way to industry. So I know Volkswagen is doing some phenomenal work on using quantum computers to make more efficient batteries, and medicine is seeing this huge boom. I think the Terrell came in here, Terrell France, and he made a great point about how this current coronavirus pandemic has really spurned a lot of interest in quantum computing. Samarth can speak a lot more to that. He's done some awesome work there as well, and it's just you just got to keep your head up and follow the news. It's every day there's always something new. So and the more experience you get with this, like the opportunities to contribute to this field are enormous. So like regardless of where you are and in terms of your experience, it's particularly accessible too, considering IBM, Righetti, I think I don't know if Xanadu does it, but some of the companies have allowed public access to their computers as well, which is very nice. So
yeah, sadly Xanadu doesn't.
Oh, phooey. Okay. Well, I mean, they
they
have their simulator.
Yeah, I want to use it.
Thank you everyone for coming out to our first meeting. This is the first time that we have done such an arrangement, and we're incredibly happy to see the number of people who have come and are interested in learning more about quantum computing. So stay tuned. And I guess, Samarth, I think I'm going to go ahead and wrap things up. If there's any closing remarks you want to make.
I think you wrapped it up really nicely, man. Thanks everybody for coming, and yeah, hope you guys can come for next week's meeting as well, when we start to get more into the actual the nitty gritty. And
the good stuff.
The good stuff, yeah. And yeah, hopefully within a little while, you guys will be able to start coding and doing some interesting things to better understand these systems and interact with them.